So today we will discuss about ordinary differential equation. Ordinary differential equation occurs everywhere. Whenever we try to model our physical systems, we don't even know how the system will behave, but we know what are the external forces, what are the guiding forces that will make the system to follow some particular trajectory. Let's take the example of uh, motion of bodies, which is governed by Newton's laws of motion. So Newton's law of motion is basically a formulation of system in terms of an ODE. It is given as mass times acceleration is the net force that is being acted on the system. So this is a differential equation. So naturally, differential equation comes whenever we try to model any rate of change, any what should I say, gradient. In all these scenarios, the differential equations comes naturally. So in this discussion we will actually see what information are actually given to us when we are given an ODE, because given an ODE our main aim is to solve it. So the existence, uniqueness, all these results for an ODE exist if we know the value of the function at some particular point, or some higher order derivatives at some particular points. So in this discussion we will basically discuss, our main aim is to discuss what are the constraints that are being imposed by an ODE. So it has been assumed that people know basic calculus, they know what is a function, what is the derivative of a function, what is the integral of a function. So all these things has been assumed so that we can start directly from the topic. So we will start from an important result in calculus known as fundamental theorem of calculus. The theorem is actually fundamental because it basically relates the derivative of function with its antiderivative. So it says that integral of the derivative of a function from say x is equal to a to b is the change of the function value at the endpoints of that interval. So in this is basically in mechanics, people would have seen this equation v dt is equal to where v is the instantaneous velocity of the particle, and if we integrate the velocity from time interval t1 to t2, it basically tells us how much the object has moved from time t1 to t2. This is what the speed is. Similarly, the derivative is the rate of change of a function as x changes. So if we know the rate of function everywhere, and if we integrate it from t1 to t2, or we sum it across different intervals, so it basically tells us in those intervals how much the function value has been changed from the starting of the interval to the end of the interval. So we will not prove this theorem rigorously, but we will try to get insights from it. uh, Suppose we have a linear function. In linear function, the slope, the derivative of the function is constant everywhere. We can write f dash x as some constant m, which is given as tan theta, basically the slope of the function, which is constant over across all the points. So suppose this is the point A and this is the point B, then we know from the straight line algebra that we can write it as fx minus fa. The slope of the function is exactly the uh, change in the function from a to x divided by the change in the interval. So we can write fx minus fa is equal to m x minus a. But this m is, so first we can put x is equal to b in the above equation, then we will get fb minus fa is equal to mb minus a. But m is the derivative of function, so f dash x b minus a. I can put tilde to suggest that this x tilde belongs to the interval a comma b, and this is exactly f dash x bx from a to b. So we can see that if we are given a linear function, then trivially we get the result fb minus fa, the rate of change of the change in the function value at the endpoints is the integral of the derivative from a to b. Basically, what is an integral? Integral is the accumulation of the function in the given interval. So if we are required to find out the integral f dash x from a to b, this is basically saying how much the function has been accumulated from a to b over an interval ab. So this characterization of integral as an accumulation will be used extensively in fluid mechanics. So now suppose we are given a function slightly modified from above. Suppose I have a function like this, which has constant slope across the interval a to x1, but after x1 its slope changes, but again it becomes constant over some subinterval of length x1 x2 of length x2 minus x1. So this is the kind of the function, and this is our final point p. Suppose this is xn, this is x3, in between there are many subintervals. So over the interval ax1, the slope of the function is constant. Say suppose the slope, so the derivative is say m1. From the interval, in the interval x1 x2, say it is m2, here it is m3, and here say it is mn. So again we can apply the above result. uh, Earlier we have assumed that the derivative of the function or the slope of the function is constant across the interval ab, but now and we get this result. But now we assume that over the interval ab the slope of the function changes, but there exists some sub interval over which the slope is constant. So for the sub interval a comma x1, we can write f x1 minus fa is uh, m1 x1 minus a. Similarly, for the subinterval x1 comma x2, it is fx2 minus fx1, m2 x2 minus x1. So we can reach up to the last subinterval. It is fb minus fxn. So we are assuming that there are n subintervals. So we got these n equations, so we can add them. So as we can add, so we can see that these terms get cancelled away. This term will cancel away with this, because the next equation will be fx3 minus fx2 is equal to m3 x3 minus x2. So fx2 will cancel away, similarly fx3, and in the end fxn will cancel away, and we are left with fb minus fa is equal to m1 x1 minus a plus mn b minus xn. So here we can see that the derivative of function in the interval a comma x1, the derivative of function exists everywhere and it is constant. But on the boundary at x1, in on the left hand side the derivative is m1 and on the right hand side the derivative is m2. So at point x1 it is not defined because left hand limit and right hand limit are not same for the derivative. So at x1 x2 x3 xn the derivative of function is not defined, but these are finite points. So for for the current discussion we can assume that there is no problem at those points. In general it is a problem, but there are finitely many points, so we can neglect that problem. So in calculus it has been said that if the function is continuous, is piecewise continuous, but if it is not continuous at finitely many points, then again the integral of the function exists if the function is integrable. So these points where the function is discontinuous does not create much worry for us because they are finite. So I can safely write my right hand side as integral of f dash x1 tilde dx from x is equal to a to x 1. So this is exactly m1 x1 minus a x1 to x2 f dash and xn to b f dash xn dx, where this x1 bar belongs to a comma x1 because actually it should be open interval a comma x1, but we don't care much about this. We can take x1 bar to be in closed interval a comma x1 even though the function is not differentiable at point x1, so we don't care about it, at least for the current discussion. If we go in real analysis, so what people do is they consider some epsilon neighborhood of x1. In the epsilon neighborhood, if we take the limit epsilon tending to 0, then the integral of the function under that interval a minus epsilon x1 minus epsilon comma x1 plus epsilon, that integral itself tends to 0. So so this uh, so this uh, way of reasoning of going from open to closed interval is sufficient, like it does not cause much trouble. So similarly x2 bar belongs to x1 comma x2, xn bar belongs to xn comma b. But now I can write the above this whole summation as x is equal to a to b because the first term is the integral running from a to x1, next x1 to x2, next term would be x2 to x3, and last is xn to b. So if we add them, then by the property of integral it will just become integral from x is equal to a to b f dash x dx. So again we get fb minus fa is equal to integral f dash x dx. So we have taken two cases. So we have taken two cases. First is the linear function, and another is the function with constant slope over some subinterval. So we can see that if this x1 becomes closer and closer to a, similarly this x2 is becoming closer and closer to x1, meaning the length of the subinterval, if the length of this subinterval is going to 0, then we can capture any general function, because a general function would be of the form this, where the derivative of the function at all the points is changing. So we can assume that it is constant over some subinterval, and then we can take the length of that subinterval going to 0, and we will get the above result, and we will get exactly the same result this for general function. So here we have illustrated only for linear function and the function which is piecewise linear. So but in general also this will hold if we take the limit of the subinterval going to 0, but this requires some arguments, some argument of proofs. Interested people can always look up in any real analysis book or calculus book. They would have proved it using mean value theorem and the property of Riemann integration. But for the current discussion, the proof is not uh, important. Important is the result, what the result is saying. So the result says that the accumulation of the derivative of a function from over an interval is basically the change in the function value at the endpoints of the interval. So the result is simple. So now we can see that if we know the derivative of the function everywhere for all x in the real line, then we actually know the function value up to a constant, because we know if we know f dash x everywhere, this g function is a known function, then at any point x naught, x naught is not a good notation, uh, then and at any point x, I can write f dash x dx from x naught to x. uh, Here this x bar is a dummy variable which is uh, integrating variable. So we can see that fx minus fx naught is equal to the accumulation of the derivative over the interval x naught comma x, but we know what is the derivative of the function, that is just gx. So fx would be fx naught So this x is a general point. So if we know the value of the function at any point x naught, then I can calculate my f at any point x as fx naught plus this integral. So this is so the evaluation of this function is just a problem in integral calculus, meaning we just have to evaluate this integral to get the function value. So we can see that what is this? Here we are given the information that f dash x is some function g of x which is a known function. This is a differential equation. This is a particular kind of differential equation where we know exactly the value of the derivative of a function everywhere, and if we know the value of the function at any point x naught, then we know fx also. So we can see that if we know the value of the function at any point x naught and the derivative of function everywhere, then we can determine the function f uniquely everywhere. This is a special kind of differential equation. In general, a differential equation is a relation between, say, suppose suppose I have a first order differential equation. First order differential equation means the highest order of derivative in that equation is 1. So in general, any first order ODE can be represented as f dash x fx is some function hx. This is the general representation of a first order ODE. It relates f dash f and x with some known function hx. Hx is a known function. So in general, uh, this function g can be very complicated function. So we can take an example. So so suppose my differential equation is a f dash x plus b fx is equal to c, where a, b and c are constants. So we can see that here f dash and f can't take any arbitrary value. They have to take values such that this relation has been satisfied, this equation has been satisfied. So so this is basically linear equation. We can put fx is equal to say z1, f dash x is equal to z2. So the above equation will just become a z2 plus b z1 is equal to c. This is a linear equation in the variable z1 and z2. So if I make so suppose if x-axis is z1 and y-axis is z2, so this is just a line in z1 z2 plane, because we know that if we try to solve this equation, there is just one free variable. From linear algebra people will know that this z1 can take any value and z2 will take the value depending on the value that z1 takes. So z1 and z2 can't take any arbitrary value, so they will take the value such that the solution, the point, will lie on this line is at one, or we can see that this is just an equation of line with the slope uh, b by a and intercept minus b by a and intercept c by a. So but z2 is our f dash and z1 is f. That means the function should be such that the function value and its derivative lies on this line. So this is the constraint that is being imposed by this differential equation. Now f and f dash can't take any arbitrary value. They have to take value such that it stays on this line. So uh, so if we have this differential equation a f dash x b f x is equal to c. So suppose we also know that at some point x naught the value of the function is f naught, then we can easily solve this by the method of integrating factor. We can write this as f dash x plus, we can divide throughout by a to get c by a. Now we can multiply e to the power b by a x on both sides. So but now I can pull the derivative out. So the LHS is just dy dx because by product rule of derivative, we know that first we have to apply d by dx to e to the power b by ax. B by a will come in front, leaving us with e to the power b by a fx. After that, we have to take derivative with respect to f, so it will become f dash. So it is just a technique to take the derivative out. But now this is some function f tilde of x. I now this is e to the power b by ax. This is a known function. C, a, b, these are the known constants. So the RHS is known, and we know the derivative of the f bar x. So again, by fundamental theorem of calculus, I can integrate both sides, and from the interval we will integrate from the interval x naught to x to get f bar x minus f bar x naught is equal to integral from x naught to x c by a by dx bar. So this f bar x is uh, e to the power b by a x fx minus that is this integral, say this integral I, and this I is a function of x. So because this x is a variable here, so the value we will get is a function of x. So this will give us fx is equal to e to the power minus b by ax uh, multiplied by ix plus e to the power b by ax naught fx naught. This is how we have solved this differential equation. So we can see that fx, it is not that fx can take any arbitrary value. It has to take arbitrary value. It has this functional form. This functional form is such that it satisfies this constraint. So given an ODE and this function value at some point x naught, we have solved the differential equation uniquely. So earlier we have this relation a f dash x plus b fx is equal to c, where a, b and c are constants. So this is basically a line in, if I consider f and f dash plane, because in general f can take any value, f dash can take any value, but by this relation f and f dash have to take values such that it stays on this line. Suppose now we are also given the information fx naught is equal to f naught. So we can see that suppose at x naught, this is the value f naught. Now because at x naught the value of the function is f naught, then f dash x naught can't take any arbitrary value. It has to take the value such that this relation is being satisfied. So we can see that f dash has to take this value. So this is our starting point. Now as I change x, f will also change, f dash will also change. So this point will also change as x moves. This point will also change. Either it can move here, it can move here, but it has to stay on this line. So we can think that given this information fx naught is equal to f naught, we get a point on this line. Now I can move any way I want. Either I can move from here to here fastly, here to here, I can move here to here slowly and then fastly. I can move in any way, but the only constraint is that I have to stay on this line. So we will see that actually we don't have freedom to move in any way on this line. There is a unique way we can move on this line. So so the suppose this is our point P. So from point P I can move either this way or this way, but we can see that if we move in the left hand side, the function value will decrease, but the derivative of the function is positive. We know that if the derivative of function at a point is positive, then as x increases, the function has to increase. It can't be that function decreases as x increases. So suppose we know that f dash x naught is equal to some constant c naught which is greater than 0, but f dash x naught is fx minus fx naught divided by x minus x naught with limit x tending to x naught. If the derivative of the function is greater than 0 at x naught, we know that also if I move at if I move in the direction x naught plus plus, that means in the increasing direction of x naught, denominator is always positive. For this left hand side to be for the left hand side to be positive, we can see that RHS always has the positive denominator, so numerator has to be positive. This means that fx should be greater than fx naught in the vicinity of x naught, like when x is very close to x naught. So we can see that uh, if I am here, the derivative of the function is positive, so there is no, we can't move in this direction, because if we move in this direction, then the function value will decrease, but the derivative is still positive. So the only choice for us is to move in the positive direction, because the derivative is positive. So as x increases, the only way we can move is in the right hand side if the derivative, because the derivative is positive. So so uh, over this line we don't have infinitely many choices to move. There is a unique way to move on this line, and that unique way corresponds to the form of the function which satisfies this differential equation. So in the next lecture we will start with this differential equation and try to qualitatively see why the solution of this differential equation is unique if we are given the value of the function at some point x naught. Previously we have seen this by an algebraic way of this method of integrating factor to come up with a unique solution. This is the unique solution. But in the next discussion we will see qualitatively how this equation guarantees us unique solution if we know the value of the function at some point x naught. So in the next lecture we will take the discussion further. So okay then.